Hi there, StudyBuds! This is your StudyBud Lyle, and join us in today's journey to the extremities. In this video, we will be talking about the founding concept of calculus, limits. By the end of this video, our StudyBuds should be able to define intuitively what a limit is, know one-sided limits and not one-sided love, and have an intuition on how to find the limits of functions graphically and numerically. So StudyBuds, ready, sit, go! Most calculus courses, if not all, kick off with limits. Knowing that, we must have an intuition that is very crucial in the field. Remember the paradox of precision through approximation in our last video? That's ruled by limits. Perhaps the most important thing to remember when dealing with limits is that finding a limit in math, under any circumstance, shows where the value of a function, a graph, a sequence of numbers, or even physical operations is headed, whether it will reach that point or not. Consider cutting your ruler in half. Then, cut what remains in half. Then, cut it again in half. It gets shorter, right? If you are going to do this infinitely many times, you'll end up having no ruler at all or a ruler of length 0. Although doing so is practically impossible, theoretically, that's how it works. Cutting the ruler in half infinitely many times is headed to give a ruler of length 0. Therefore, the limit is 0. Another would be the sequence of 3.1, 3.01, 3.001, 3.0001, and so on, with a pattern of 3 plus 1 over 10 raised to the power of n. As the sequence progresses, the number after the decimal point becomes more and more negligible. Clearly, the sequence is headed to the number 3, and that's the limit. Let's stop beating around the bush. For example, we have the function y is equal to 3x minus 1. And we are interested in what's happening to the value of y as we let the independent variable x approach a certain number, say 4. Remember that we don't have to reach 4. We just need to approach 4 from both sides. Numerically, it will look like this. On the number line, on the left side of 4, we have the values of x to be 3.9, 3.99, 3.999, and so on, with a pattern of 4 minus 1 over 10 to the power of n, and their corresponding y values of 10.7, 10.97, 10.9997, and so on, with a pattern of 11 minus 3 over 10 to the power of n. While on the right side of 4, we have the values of x to be 4.1, 4.01, 4.001, and so on, with a pattern of 4 plus 1 over 10 raised to the power of n, and their corresponding y values of 11.3, 11.03, 11.003, and so on, with a pattern of 11 plus 3 over 10 to the power of n. Clearly, from both sides of 4, the value of y approaches 11. Therefore, the limit of the equation y is equal to 3x minus 1 as x approaches 4 is 11. In notation, it will look like this. This reads as the limit of 3x minus 1 as x approaches 4 is 11. But wait! We can simply substitute 4 in the equation and the result will still be 11. So, why did we have to go through all of this? Well, we're just lucky that our example is a polynomial. So that means, if we have a polynomial, and we need to find its limit as x approaches a certain number, we can immediately evaluate the limit by substituting the number to which x is headed. In notation, p of x is equal to p of c, where p of x is a polynomial and c is the number to which x is headed. Note that p of x strictly needs to be a polynomial whose domain is unrestricted. If it's not the case, then you can't simply substitute c. We will discuss more about this in the next video on limit laws. We have also mentioned that it has to be the limits from both sides. True limits exist only when the limits are two-sided. The left-hand and right-hand limits converge. Fortunately, in our example, both the left-hand and right-hand limits equal to 11, according to the table we made earlier. In notation, the limit of 3x minus 1 as x approaches 4 from the left is equal to 11, and the limit of 3x minus 1 as x approaches 4 from the right is 11. See the extra plus and minus signs? The minus sign means that it's the left-hand limit, while the plus sign means that it's the right-hand limit. But are there cases where the left and right-hand limits do not converge? The answer to that is yes. In our next example, we have the piecewise function f of t. Here, we can see that as t approaches negative 2 from the left, the function approaches 0. In notation, it looks like this. The limit of f of t as t approaches negative 2 from the left is equal to 0. Now, how about when t approaches negative 2 from the right? The function also approaches 0. In notation, it looks like this. The limit of f of t as t approaches negative 2 from the right is equal to 0. Since both the left and right side of negative 2 approach the same number, which is 0, we can say that the left and right hand limits are equal to 0, and that the limit of f of t as t approaches negative 2 is equal to 0. Now how about when t approaches negative 1? From the left, we see that the function approaches negative 1, and in notation, it looks like this. The limit of f of t as t approaches negative 1 from the left is equal to negative 1. From the right, we see that the function also approaches negative 1, and in notation, it looks like this. The limit of f of t as t approaches negative 1 from the right is equal to negative 1. We have the same case as the previous one, where both the left and right hand limits approach the same number. Therefore, we can say that the left and right hand limits are equal to negative 1, and that the limit of f of t as t approaches negative 1 is equal to negative 1. Now, let's try to find the limit of f of t as t approaches 0. From the left, we see that the function approaches negative 1. In notation, we write it as the limit of f of t as t approaches 0 from the left is equal to negative 1, while from the right, the function approaches 1. In notation, we write it as the limit of f of t as t approaches 0 from the right is equal to 1. Since the left and right hand limits do not converge, we say that the left hand limit is negative 1 while the right hand limit is 1. And since the two values are not equal, therefore, the limit does not exist. Expect more of these when we discuss the concept of continuity in the future. Are you still there, StudyBuds? Let's take our discussion slowly so that all the information is well absorbed. Just a quick recap. The most important things that we must remember from this video are these. First, Finding a limit in math under any circumstance shows where the value of a function, a graph, a sequence of numbers, or even physical operations is headed, whether it will reach that point or not. And lastly, the limit at a point only exists when both its left and right-hand limits converge. On our next video, we'll focus more on the analytical part of finding limits and discuss limit laws that will help us find limits with much more ease. I hope you learned something today, StudyBuds. This has been your StudyBud Lyle, reminding you to study well. Till our next trip to the StudyWorld.